Hi there. Today we want to take a look at an object that is on an angled surface like a ramp, but is being dragged, or in this case is actually just sliding along the surface. And it's a rough surface, so it's going to have some friction. Let's say that we're answering a question something like a 34 kilogram box slides down a 27-degree ramp with an acceleration of 1.38 meters per second squared. Acceleration due to gravity is 9.81 meters per second squared, and we want to find the coefficient of kinetic friction between the box and the ramp. So let's see, we have a 34 kilogram box, and it is sliding down a 27-degree ramp with an acceleration of 1.38 meters per second squared. 1.38 meters per second squared. All right. Um, G, sometimes I'll use 9.8. If I'm working the homework, I always use 9.81 meters per second squared. So I'm going to write that there as a reminder to myself. And we're looking for mu, specifically mu k. All right, so we want to know exactly what the measure of friction is between these two surfaces. All right, before we do anything else, we've got our givens written. Let's make a little drawing of some free body diagram here. Let's get a little some forces. All right, we always know that gravity is acting on the object, and we always know that gravity is acting straight down. So I'm going to draw that in place, acting straight down, even though that's angled to the surface. Now we also know that there's going to be a normal force provided by the surface, and we know that by definition that is perpendicular to the surface, which means it is not in line with gravity. All right, since the box is going to be sliding down the surface, we know that friction will be acting up the surface because friction always opposes motion or attempted motion. And so even if it were not moving, friction would still act up the surface because friction always opposes attempted motion as well as motion. And so gravity would be trying to move it down the ramp, and friction would thus be acting up the ramp. So let's label those real quickly. That was our normal force provided by the surface. This was our frictional force. This is our force due to gravity. Ooh, that's an F, I promise. Okay. And now the real question that students want to ask is, where is the applied force? Well, in this case, there's no external applied force. There's no worker. There's no no dog or little gnome pulling on the box. There's just going to be gravity. So gravity is what we're going to be counting on to move the box. In this case, we're going to use our alternate xy axis. We're going to keep our xy axis in line with our surface rather than with the ground, the surface that the object is moving along, so that it can move in only one dimension at a time. Which means that gravity is what's not in a single dimension. And so we'll need to break it up into components. Let's do that real quick. And so we'll have FGY, which will tell you what, let's make these dotted so that we can tell that they're the components. So we're going to have FGY acting right there, and then FGX. Okay, so we've got FG, FGY, and FGX, and this, of course, is in our new y dimension, and this is in our alternate x dimension, so FGY and FGX. All right, at this point we need to begin looking at what might be equal to what and writing down and doing some calculations. Now I know that FG is going to equal m times g. That's always true. And once I make that calculation, then I'll be able to use sine and cosine functions in order to find FGY and FGX. We'll do that shortly. Let's see. Now, I can see that in the y dimension, the object is balanced, and so I've got FGY equals Fn. So FGY equals Fn. In the x dimension, I can see that, well, there's only one force. Excuse me, sorry about that. There are two, and it's just that easy if you don't have a good free body diagram to make a mistake. So FGX is acting down the ramp, FF is acting up the ramp. It tells us the object is sliding down the ramp, so we can know that FGX is either equal to or larger than FF. And so it turns out that the net force is always the bigger one minus the smaller one. So F net is going to be equal to FGX minus FF. Great. Now let's see, two other things that we know that are always true. We know that F net is always equal to M times A, and we also know that mu is equal to FF divided by Fn. All right, and since we're actually looking for mu, this is likely going to be our finish line, so we'll need to find FF and Fn. Let's see, I could find FF from this equation, and I could find Fn right here as soon as we find FGY. So let's go ahead and find FGY. I'm going to take a moment and do some calculations, and why don't you do the same. Go ahead and calculate FG, and then with theta right here, remember that due to miracles of geometry, this theta in this triangle is exactly equal to that one, so they're both 27 degrees. So take a moment and find FG, FGY, and FGX.